Hi, and welcome to my channel, JaberTime. I'm going to go over limits and continuity. The definition is kind of lengthy to read. We're going to use it later on in one problem. And I have also the limit concept without epsilon and delta. These graphs shows your domain and range. Your domain is on the XY plane, and your outputs are on the Z-axis. So L and L plus epsilon and L minus epsilon, that's an interval with a radius of epsilon with the center L. This is a 3-dimension graph. So when you have a disk right here, that's called D delta, a disk with a radius of delta, and the center is AB. If I say that the limit as x and y approaches A and B is L for any epsilon that you find for me, even so tiny, I will find a disk right here. That means I'll look for the correct radius, being called delta. That will be mapped to this interval within it. So in general, instead of giving me numbers and I'll give you back numbers, you say I'll give you epsilon, then I'll do the math and I'll work backwards. I'll make a connection. I'll find the right radius right here. That will make sure that I am within the limit with a radius of epsilon. Okay, enough talking about the formula and the graph, so let's get into it. Oh, before I move on, I just want to give you an advice. Limits and continuity, it's a topic, especially when you talk about advanced problems. It takes time and takes practice. Probably this is one of the videos that you're gonna end up seeing more than once. You know, some videos are usually straightforward. You kind of like see like, I don't need to watch it all the way. But for some others, maybe. With limits and continuity, you need probably to see it more than once. Seeing enough examples like 5 or 6 or 8 is not enough. Seeing one problem with limits involving epsilon and delta is not going to be enough. I don't think one video will cover it all. So I can't here show you like 7 limits of epsilon and delta. That's what I mean as a concept. So let's move on. In calculus 1, we have the limit of f of x as x approaches a from the left, and we have the limit of f of x as x approaches a from the right only. So we approach a from right and left. That's pretty much it. We have a white plane on the whiteboard. Let's say it's just like plane x and y axis, and we approach 5 from right and left, and we just try to find the limit. If they both agree, we're done. If they don't agree, we say the limit does not exist. Now we have x and y approaches a and b from many different directions. Infinite number of directions. You could approach it from this line aligned with the x-axis. You could approach it with this line aligned parallel with the y-axis. You could approach it right in the middle if this is like kind of like in the middle with 45 degrees. You could even approach it on a curve or a function. However, if you're lucky and you find the limit of f of x, y as x and y approaches a and b on some curve, some path, C1, to be L1, and you find it on a different curve to be different, that's why it's called L2, instead of calling it L1 again, then we're done, case closed. Limit of f of xy as xy approaches ab does not exist. Let's take some examples. Now, if you've never seen this before, you might say, like, how do I start? Well, that's my point. You gotta see enough problems, write some notes, practice, and come back to it. To me, it's well balanced, x's and y's, except the negative is for the y. So let's go along the x-axis, because we are approaching the origin. So with these examples, we're just approaching the origin. Imagine if we are approaching 3 and 2. That's going to be second level of types of limits. So I'm going to focus on the concepts more. When it's algebra, I'm just trying to speed up the process and save you some time. Our function, before I apply the limit, you could just say, you know what, I'm just going to put y equals 0, because along the x-axis, that means y equals 0. So this is gone, so the negative did not do anything for me. I end up with x squared over x squared, which simplifies to 1. Now I could simplify this. Why? Because x approaches 0 and x cannot equal to 0. So I could divide both sides by x to the second, just because we are approaching 0. As you can see, to emphasize that, I did it right, and the answer is 1. Now, if your simplified function along this path is 1, the limit is not going to go anywhere else, so the limit is 1. Along the x-axis or along y equals 0. Let's go along the y-axis. That means x is 0. Well, in this case, look, if these cancel because x is 0, the negative stays, which means your reduced simplified function is -1, and the limit is -1. So L1, L2 are not the same, which means the limit does not exist. Let's take another example. Kind of well balanced, as you could see. Doesn't matter if x is in the front or y is in the front. They are kind of like both the same on the graph as an effect. Along the x-axis, so y is 0. This is going to be gone. This is going to be gone. This is going to be in my way, approaching 0. We'll see how it's going to go. So we have 0 over x to the second, but x to the second is not equal to 0. We are approaching it, like 0 over 0.0001 to the second. That is 0. Let's go along the y-axis. I said earlier, just by looking at it, it doesn't make any difference. You're going to this time put the x equals 0. And you end up with 0 over 0 plus y to the second. Same style. 0. Now, let's go along y equals x, like a 45 degree in the first quadrant, approaching the origin, towards the origin. Let's see what's going to happen. You could replace y with x, replace this y with x. You could see what happens. So it's x to the second over 2x to the second, which reduces to half. So the limit, there is nothing here to apply. It's going to stay half, which is different than zeros. So the limit does not exist. Here's another example. This time the y's has more. Let's try and speed up the process. Instead of going along y equals x, along y equals 5x, along y equals 7x, we cover them all and call it y equals mx, where m is just a slope. Doing the math, this is m and x to the second, so m squared x to the second, so it's going to be m squared x to the third, x to the second, m to the fourth, x to the fourth, factor out x's, I don't know if I said y, x's, x to the second out, reduce it to the following. This approaches 0, this approaches 0, so it's 0 over 1 plus 0, 0 over 1, 0. Let's go along y to the second equals x. This is like a parabola if this is the origin. A parabola that opens, a parabola that opens to the right. Usually we see it as y equals x to the second, not x equals y to the second. So that's a parabola that opens to the right. Now you might say, why you think this way? I said early, enough practice will give you hints. Look at this, and look at this, and if you replace that y to the second instead of x, this is going to be y to the second. It's going to make it like this, so I could combine them, which is right there. Reduces to half, because I could do that, because y is approaching 0, it does not equal to 0. I keep repeating myself. And the limit is half, but it's different than 0. Case closed, the limit does not exist. One more example. 3x to the second y over x to the second plus y to the second. Along y equals x to the second. Regular parabola that opens up. Just do the math. For y, write x to the second. Simplify your function before you apply the limit if you want. Take out x to the second. Divide by x to the second, because you can. And I have the following. Now apply the limit. I get what? 0 over 1 plus 0, which is 0. See right here, I wrote x approaches 0, not x and y approaches 0, 0, because there is no y anymore. Let's go along x equals y to the second, the parabola that opens to the right. Now, instead of x, write y to the second. This time I had the limit in my way. Simplify, factor out y to the second. Cancel it, because you can. 0 over 0 plus 1 is 0. So now what? Sometimes the limit exists. We could try it again and again and again. Go along the x-axis, go along the y-axis, go along y equals x, which makes it kind of like hard for some students to think like, where do I go from now? Should I just keep trying? Well, if you have the time, you could just keep trying. Or if you have a feeling that it might be the limit, we need to prove it. Sometimes to make it easier on you, we kind of give you problems that are similar or easier to follow. And if it's too long to investigate, we might say prove that the following has the limit so and so. In other words, go ahead and use Epsilon-delta. Instead of wasting your time, we try to tell you. So here we go. So with that, does the limit exist? And if it exists, is it 0? Like, is it our limit, 0, 0? This is the slide that I'm going to slow down because it's worth it. And I cannot do like too many problems of this in one video. I have another limit problem with Epsilon-delta in Calculus 1 from summertime. I'll put the link in the description below so you could visit that. And it's at the end of the video, by the way. It's worth it to see more and more to practice limits. So here we go. One more time, I'm going to slow down here just because it's worth it. The limit that was written earlier on the front page is the following. Let epsilon be greater than 0. We want to find delta greater than 0 such that x squared plus y squared, or x minus a to the second plus y minus b to the second, which is a distance within a disk inside from the center A and B. In our case, we're approaching 0, 0, so I don't have A and B. It's just x squared plus y squared. We want to find delta. That will force me to end up with my outputs for those x's and y's that I'm dealing with, that they are within a radius of delta, to give me outputs that are within the limit 0, because we are assuming that the limit is 0, could be 5, is less than epsilon. So it shoots only within a short interval centered at L with radius, because it's an interval that has a center. So that's why I'm using the word radius of epsilon. But the absolute value right here doesn't do much for this guy or this or this or this. And I don't need to keep the minus 0 in my way. So the problem becomes, in short, the following. I just need this absolute value to be applied to the y. Because this is positive, this is positive, positive, positive. I don't need this. Gone. This right here is, in short, right here. So epsilon is given to me. This package is less than epsilon. We're trying to find delta that talks to these guys. It's a radius. Here we go. This package is given to me. Let epsilon be given. We want to find delta. I'm gonna start on the left. That's my left. I wrote y to the second at the bottom side in green. I want you to look at y to the second. Y to the second is greater than or equal to 0. We agree on it, right? Now, looking at this right here, without the 3, without the absolute value of y, it's called x to the second over x to the second plus y to the second. Because this could be 0 and could be more than 0, it's being squared, this fraction will be less than or equal to 1. If it's 0, if the y is 0, this will be 1, the fraction. And if it has some numbers in it, like let's say 0.001, that means the denominator has more than the numerator, so it ends up less than 1. So keep this in mind. This right here is less than 1, which means this whole package is less than or equal to 3 times 1 times absolute value of y. From algebra, we know that the absolute value of y is the answer to the square root of y to the second. If you don't know what's y, you have to be careful and write y to the absolute value of y. This is not our topic, but I'll go over it quick. If y is 5, this will be 5 to the second, which is 25. Square root will be 5. So the absolute value was not needed. If y is negative 5, when you square it inside, it becomes 25. When you take the square root of 25 on a calculator, it's just 5. So what happened to the negative we started with? Hopefully get my point instead of skipping the whole thing. Now, I could replace this with this. I just did. If you don't know why I'm doing this, take a look here and you will see where we're going. Here's another concept. The square root of y squared is less than or equal to square root of x squared plus y squared, which is true. If this is 0, they're going to be equal. If this has something in it, that's not going to be equal. This is going to be more. So I could say this much is less than or equal to 3 square root of x squared plus y squared. But what do you know about this? We know that it's greater than 0 because we don't want the distance away from the limit 0, 0, away from a and b, which is in our case 0, 0, to be 0, because that's not a limit concept. I can't step on a, b and call it limit. The limit as x approaches a, that means you are approaching a, but you're not equal to a. That's hopefully is clear. Why do we have this in math? We don't have it here, but we have it here. Okay. We know this. Let's take this out of our way. We don't need it for now. Let's look at this and look at this. That says if this is less than delta, that means 3 of this is less than 3 delta. I have the 3 here. So 3 square root of x squared plus y squared should be less than 3 delta. But this is less than epsilon. That is the connection. And that will be almost done with the problem. We take 3 delta equals epsilon. So you give me epsilon, I multiply by 3, and that's going to be my radius. That's the whole idea in words. Solving for delta, that will be epsilon over 3. You give me epsilon, I said multiply by 3 by the way, maybe by mistake. You give me epsilon, I'll find delta, which is 1/3 of the epsilon that you gave me. That's the right way to say it. Hence the limit does exist, and this is a proof. Going over it again and rephrasing it might confuse some students. I would rather leave it this way, and I went slow enough, and it's kind of hard to slow even more, and it's hard in one video to cover more limits. Hopefully in the future, because I have a lot to do and I'm running out of time making videos for other topics and other classes, I will be revisiting and will be making more and more and more limits examples on with YouTube videos. So if you are subscribed to my channel, you're gonna see more and more. As you can see, I'm a busy man working very hard on making those videos. I'm seeing myself within a year or 2 from now with a lot of math videos simplified with examples and graphs. Hopefully get my message, and let's move on. Now I could relax and speed up a little bit. Continuity. We know what's continuous in calculus. We say like you can't lift a pencil, and if you trace it from A to B, you don't lift the pencil. You know, just to give you the concept of what's continuous. In calculus 1, we say f is continuous at x equals a if the limit from the left is L, the limit from the right is L, the point itself is defined also at L. So it's almost like it's not like they're both pointing to the same point, but that point is missing. It's also filled with the same value. And in short, we just write the whole thing here in one statement, which is the limit of f of x as x approaches a, that means right and left, is exactly the same as f of a. I don't need to write this down, but I think it's worth it, and it doesn't take time. As you can see, I was going a little bit fast. Here we have the following. If f is continuous at ab, then the limit of f of x as x and y approaches ab will be f of a and b. Same style. Now we're away from limits with epsilon and delta, so you should be relaxed now. All polynomials are continuous on r to the second. Quick example. I don't want to take the time to plug in the numbers here, 1 and 2, 1 for x and 2 for y. Using direct substitution, the limit is 11. Done. Quick. What about rational functions? You know it. You had enough math background. This is a rational function. F of x, y is discontinuous at 0, 0. Why is that? Because the denominator is not defined at 0, 0. It is continuous on its domain, which is everywhere except the origin. How about if you make it defined at 0? Because here it's not defined at 0. Keep this in mind. I'm using the same example, by the way, on the coming slide. X squared minus y squared over x squared plus y squared. Now I'm defining it at the origin to be 0. Going back to the first example in my video, we tried the limit here and it did not exist. So if the limit here does not exist, I don't need even this to be filled. It doesn't make any difference. So it's discontinuous. Just because the limit as x and y approaches 0, 0 does not exist, that means that's it. You're done. Even if it's defined here. Here's another example. Going back to example number 4 in my video, when we used epsilon-delta, we know that the limit of this was 0 and we proved it that it's 0. Now it's defined on the origin to be 0 also. So the limit is 0, which is exactly the same output as expected or wanted. So f is continuous at 0, 0. So f is continuous everywhere, and usually the domain is part of the xy plane. This is the xy plane. How about composition of functions? We did that in lower math. We're going to apply it here quick. If you have a function called h of x and y is arctan, meaning tan inverse of y over x, you could say this is two functions in one. The first function is y over x, and after I finish that, I apply tan inverse. That's my second step, my second function. So we call the first one, let's say, f of xy, which is y over x. It's continuous, except at x equals 0. Of course, because it's not defined at 0. G of t, if you want to call it g of t, is arctan t. It's continuous everywhere. The tan inverse, tan looks up and goes sideways as inverse. So it's continuous everywhere. So my original function, because it had an issue right here in part of the game, the original function, we say that our function g of f of xy, which is arctan y over x, is continuous except at x equals 0, because I can't plug in 0. It's not in my domain anyway. Functions of 3 or more variables. Limit of f x y z as x and y z approaches a and b and c is L. That's interesting. For every epsilon greater than 0, there is delta greater than 0 that corresponds to it. If your points are less than d, or belongs to the disk. In this case, we are not in a disk, we are actually in a sphere in 3D. And the distance away from A and B and C, which is the center. See, you could look at this as a sphere without the square root, right? Is less than delta, and that's my radius. Then, my outputs away from L are less than epsilon. f of xyz is continuous at ABC if the limit is exactly the same as the output at that point, just like calculus 1. Example: f of xyz is continuous on r to the third, except when the denominator is 0. But if this is 0, I could move on to the other side and I could write it this way. Have you seen this before? X squared plus y squared plus z squared equals 1. That's a sphere. So it's interesting to imagine what's happening right here. Here's the statement: or it is discontinuous on the sphere with center 0, 0, 0 and radius 1. So imagine a function that is continuous everywhere, but not on the surface of the sphere that is described right here. So it's continuous inside it and continuous outside it, but not on it. That's why I kind of like circled the on, and discontinuous is highlighted or different color to let you focus where it's not continuous. Okay, I think that should do it. I tried my best. Hopefully it was good enough. It's not that easy to cover every single aspect and cover every single example in one video that stays about half an hour. So to the best that I can, this is what I have, and we'll just keep going, and I'll see you in the next one. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.